All right. Hi, everyone. Welcome to another session of the IX seminar. We again continue our kind of deep dive into large language models, this time with Leandro von Werra from Hugging Face, which I think everyone must know who's ever used LLMs these days. So I'm very happy to give the word to Leandro. Take it away.
Thanks, Anastasia. Just to double check again, you can see my screen and you can hear me well. I guess so, if I don't hear anything. So yeah, today I'm excited to present a little bit the work that we've been carried out under the umbrella of Big Code. Big Code is an open research collaboration, and we've been trying to build large language models specifically for coding applications. And I plan to talk a little bit about three things, like first of all, what Big Code is and how it works as a community. And then we delivered so far essentially two milestones. One is a large data set for code that we called the stack. And the second part is a large language model for code called StarCoder. And there I want to talk a little bit about how we went about some of the design decisions that we had to take to build the model and what it takes to get there. So let me start by talking a little bit about the community. The main motivation of Big Code was that there was a development. We started more than a year ago, and the status at this point was that most large language models for code that were very competitive were either closed or lots of information about, for example, their pre-training data was unknown. And so Big Code, the idea behind Big Code was to essentially build large language models for code, but as a community effort. So everybody in the community can learn about what it takes to build a large language model. Since that's sometimes a little bit like the secret sauce behind the big tech labs. And so Big Code is an open scientific collaboration. Essentially, everybody with an engineering or scientific background can join Big Code. To date, we have over 1,000 members on our Slack channel contributing in various ways to the project. And they come from over 60 countries. So it's a very diverse group of people that came together to see how we can build competitive code models. When we started thinking about the project, we found that building code LLMs is not only a technical challenge. There are also many more governance issues connected to training code models or language models in general. One issue is, for example, consent of data subject. That means we're using a lot of code from people that put it on GitHub. But the question is a bit, can we use that data? What kind of options do we need to offer to make to responsibly use their data? There is also privacy risk when you train language models. You train them on lots of data from the internet or in our case on code. And these language models memorize a lot of information that's in that data, and it can be quite easy to prompt them, for example, to yield social security numbers, or more specifically in case of code, for example, a password that somebody accidentally committed on GitHub. And then there's also more specific to code models, there's software safety and security issues, right? Because we train our models on a lot of diverse code, and there can be two issues with safety and security. One, we might train on malware, so the model learns how to generate malware. And the second issue, which is maybe the even more prominent one, is we train potentially on outdated code as well, which has security flaws or known security flaws that have never been patched because the repository that we used was pretty old. But the model learns to generate code like that, so it might propagate known security flaws. We built a governance card around our efforts, so we're trying to document how we address all of these issues. In addition to like these more governance challenges, there is also some challenges related to the closed models and problems that arise when you don't disclose how you trained your language models. One thing that even most of the open language models these days don't really disclose, even open models like the new Mistral model or Llama, they don't tell you what exactly the training data is. And so that makes it difficult for a few reasons. So on the one hand, you don't actually know whether your data is in their pre-training data, right? So it's hard for you to know if they used your data, or impossible for you to know if they used your data. And if you don't know, there's also, it's hard to complain about removing it potentially. Obviously, scientific reproducibility is an issue. If you don't know what the training data is, you have like very little chance to reproduce their language models and to verify that it actually works as well, or for the reason they claim. And an issue that we quite frequently face is benchmark contamination. Since most companies don't tell you what data they trained on, it's really hard to know if they trained on some benchmarks that you want to evaluate the model on. And I'm going to come back to that a little bit later again. But that makes it very hard to actually trust the performance of models because you don't know if they've been partly trained on the benchmarks that you use to judge. In addition to that, if the models are not even open access, if they're only available via an API, that also makes research more difficult in terms of safety and alignment. You only have access to like the very last thing the model outputs. You don't have any access to the inner workings, for example, and you can't adapt the models easily or fine-tune them with your own technique. Maybe the API offers a fine-tuning option, but other than that, you're very limited in what you can do with the models. So these are some of the reasons why we, on the one hand, wanted to be very transparent about the data that we use for training. And on the second hand, we wanted to build models that we can release and people can build research on top of that. And yeah, I'm also going to come back to that a little bit, how like open models can help researchers build cool things on top. These are a few of the aspects that we thought about, but there has been like a lot of thought going into like the whole governance and responsibility aspect of training the models. On the one hand, as I said, we try to be very open access when it comes to the data set. So we only used permissive licensing for the pre-training data set. We had tools to inspect the data and to opt out. We have PII removal and so on. I'm listing here a lot of things, and I don't think I have time to go through everything, but everything here is linked, so you can go to each of these resources where we outline like how the model can be accessed. We released all our code that was used to, for example, pre-process and train the model, and we try to document as well as possible all the steps. So let me get to the first milestone, which is the stack itself. So the stack is a data set, and more specifically, the stack is a pre-training data set, so of code. And we collected it by going through GitHub, and we collected 6.4 terabytes of permissively licensed source code in over 300 languages. And on top of that, we provide tools for data inspection and an opt-out mechanism. So you can check whether you're in the data set, and you can opt out if you don't want to be in the pre-training data. So the question is, how do you create a very large data set for code? And our pipeline looks roughly like that. We start with GitHub Archive, which is an archival effort to preserve as much as possible from all the information that's shared on GitHub. And we use that to query all repository names that are available on GitHub. And we used that list, which was roughly 200 million repository names. And what you do with that list, essentially, you git clone for 3 months and to get all the data. Git cloning 200 million repositories takes a while. It took, as I said, 3 months on a cluster. And we ended up with roughly 140 million repositories. The reason there is a discrepancy between the 200 million and the 140 you end up with is some repositories might have been deleted, some repositories might have been renamed. In that case, we couldn't find them. But in any case, we still end up with 140 million repositories, 50 billion files, and 100 terabytes of data. That's a lot of data to train things, but we had to do a little bit more filtering to make sure the data that we actually have is of high quality and suitable to train a language model. And so the first step to clean up the data set is just selecting a subset of file extensions. A lot of files that are on GitHub are not necessarily code. People are also committing images or CSV files, and I mean, whatever kind of data that you want to commit, GitHub lets you do it. But we wanted to focus on just file extensions that contain code. So that already reduced the size of the data set from 100 terabytes to 70 terabytes. Then the next thing we looked at is the licenses of the data set. So GitHub allows you to provide a license for your repository. In addition, people can add their own licenses to individual files. And we decided only to use permissively licensed code for the pre-training data. What's kind of interesting, if you look at the license distribution on GitHub, there is essentially three or four categories of licenses. There's Apache and MIT, which make up maybe 10–20% of the old code available on GitHub. And then there's 80% that's unlicensed, and then you have a few percent of like other licenses, but like the permissive and the no license data is by far the majority. And we only took like the permissively licensed code, which gave us roughly 6.4 terabytes of data. And then we did a lot of analysis and ablations to figure out, now we have 6.4 terabytes of data. How should we filter them to get like high quality data? Because if you train the language models, if your pre-training data is not of high quality, then also your language model is not of high quality. I think the language modeling community kind of went full circle on the well-known fact in the data science field, which is like data quality is all you need. And I think at the beginning, people were a little bit, we just take some data, if we have enough data, we throw it at the language model and it's going to learn something. But people are figuring out more and more that the higher quality your pre-trained data is, the higher quality is going to be your language model. Not so surprising if you think about it, but quite an important fact. And we tried to see like very different approaches to figure out what's high quality data in terms of code. We looked at the code and comment ratio. So do we get a better performance if we look for like a healthy ratio of code and comments? So if files only have comments or have no comments at all, maybe we exclude them. But if they're somewhere in the middle, that's good code. We looked at, for example, GitHub stars. and a few other approaches, and we found the only approach that gave us consistently gains in terms of model performance is near deduplication. So near deduplication means that in code, we often have files that are very similar, but slightly different. For example, a config file might have changed just a field. In our pipeline, at the very beginning, we remove duplicates. So if there's an exact duplicate of a file, we don't keep it, just for the fact to save space. So the data, the 6.4 terabyte, they're already deduplicated. But if we deduplicate them further and look for near matches, that improves the performance of the language model further, and we can see that also shrinks our data set size considerably. So we go from 6.4 terabyte to 2.9 terabyte of data. We released both data sets, so people can also try their own filtering techniques or their own near deduplication pipeline. But we used the latter for our experiments as a starting point. I mentioned that we have tools to see, to investigate the data set and to potentially opt out. One of them is an app that's called MI in the Stack. And how it works is you go to that website, I linked it here, and you enter your GitHub username, and it will tell you which repositories are in the stack. And you can see here on the right-hand side, that's my username, and you can see there are 5 repositories from my account. And if you wish to opt out, there is a link that leads you to a GitHub repository, and if you open an issue there, in the next round of training, you're going to be excluded. We had someone in the Big Code community doing some research on how the developer community feels about like training on their code. And what's kind of interesting is that people opt out for many different reasons. So some people believe such an effort should be by default opt-in rather than opt-out. From a language modeling training perspective, that's like a very hard thing to do because we need very high volumes of data. Otherwise, you can't train a language model at all. And so an opt-in is like, for us, like even technically not really feasible. But there are people thinking about like how to set up such a thing that maybe over time you gather enough data that you can train on a fully opt-in data set. Others feel like it's unfair to use their code without compensation. There's like a slight variation of view depending on if you talk about like a closed model like GitHub Copilot, which earns money with it. Some people feel okay if the model itself is also like open source, and so they can that the whole community profits from it. Some people are afraid that there's too much PII in their code, and they don't want to be publicly exposed. So PII is personal identifiable information. Funnily enough, some people think like their code is not of good enough quality, and they feel like they're hurting us by considering their data or their code in our training. And some people just feel like not very confident about the state of code generation, and they're a little bit concerned that somewhere a language model might produce like some code that belongs to them, and they could somehow be traced back to them, and maybe it's produced in the wrong context. The conclusion a bit of that research was that most people don't actually want to opt out, but they want to know if they're in the data, and they want to have a choice. So even if they don't want to opt out, they want to have like the option to opt out. And I think we try to address that with both the MI in the Stack tool and the opt-out forms. So I talked a little bit about what it takes to get a data set to train a language model, and now I want to get to like the more exciting part, which is like how do you actually train a language model for code? And I want to talk about StarCoder, which is the last model that we trained. So for StarCoder, we took that data set I talked about before, after the license filtering and removing the duplicates, but we added a little bit more filtering on top. So we have these 2.9 terabytes of data in 300 languages. But we were a little bit worried that it's a little bit too much data, and maybe we can still improve the quality a little bit over just doing near duplication. And so we did a few things on top of that. The first one is we selected roughly 80 to 90 languages out of the 350 languages. We were mainly worried about model capacity. If you've seen, for example, people trying to train multilingual language models, there's always a risk that you lose model capacity if you distribute too many languages inside one model. And so instead of going for 350 languages, we decided to go for a little bit safer number, which is 80. We try to include like still a high diversity. I think we include most popular programming languages these days. We mainly excluded programming languages that have been superseded, for example, or some of these 350 programming languages are more like configs, for example, and we try to exclude configs and things like that as much as possible to focus on code. In addition, we applied heuristics to filter the code a little bit. There's quite simple heuristics that you can apply that improve the quality quite a bit and give you better model performance. One is to look for auto-generated data. That can be a very simple filter that looks for the words auto-generated in like the first five lines of code, and that already gets you a lot of auto-generated code. Other ones are looking, for example, at the average line length or the maximum line length. That's also an indicator for if the code was auto-generated or was written by a human, because we tend not to write very long lines consistently. And then finally, we also redacted PII. That was a little bit tricky because there is not really a PII data set or a PII model for code. And the kind of PII that we were looking for is slightly different from what you look for in natural language models. So the kind of things that we were interested in was, for example, password hashes that someone maybe accidentally committed, access keys, or IP addresses. And to get a model to filter those out is pretty hard to do with, for example, a regex. So what we did instead is we partnered with an annotation company, and we had them annotate a few thousand files for these specific fields. And then we trained an encoder model to detect those PII. And then we applied that over the whole data set and redacted the PII. For example, IP addresses we replaced with like standard IP addresses. Names we replaced, for example, with a name token. So that removed quite a bit of data again. So we went from 2.9 terabyte to 800 gigabyte, which is quite a loss. Quite a lot of that data that we lost was also partly like HTML or JSON and CSV, kind of like either verbose formats or data formats. And by subsampling or filtering them, we lost a lot of volume in terms of data, but we still ended up with 200 billion tokens. So 200 billion tokens is a good start to train a language model. Before I go into like some of the design decisions, I thought it makes sense maybe to give a small refresher on like how a GPT type language model works. And the idea of the transformer GPT models is that they can attend to the previous token when they need to predict the next token. And you can see here on the left, on the bottom, you can see that you start with a start token, for example. When you enter the first token, there's nothing yet to attend to. But once the first token is generated, in that case, my, the model can start attending to the previous token. So it gets as an input the start token and my, and it needs to predict name. And so what it can do is it can look backwards, and that's highlighted by these curved lines that flow backwards. And the further you go, the more tokens the model can attend to. So for example, if the current token is, the model can attend to the start token, it can attend to my, and it can attend to name. And then it needs to predict my name based on that. The models don't just generate the token itself, but usually they generate the probability distribution over all tokens. And then depending on your applications, you might choose a different sampling strategy to get like a better performance in generation. So for example, when exactness is very important, for example, in math, but also in code, usually you sample from that distribution with a very low temperature, or even do greedy decoding, which means you only take the token with the highest probability. But these are some of the choices you can then take when you generate. That's like the high-level view of how a transformer works, but there's some other decisions that we had to take when it came to like what kind of model do we actually want to train. And I tried to list a few things here, and we tried to take the perspective of a user or maybe a machine learning engineer that wants to use our model in production or wants to fine-tune it, and we want to like provide the best model for that use case rather than just optimizing for the model with the best performance, which might be slightly might have a slightly different architecture. So the first thing is, if it should be easy for downstream use, it should be a relatively small model. Not everybody has access to a big GPU cluster for either doing inference or optimization. So model with hundreds of billions of parameters might be too expensive and too complicated to deal with. And we thought a 15 billion parameter model is hopefully like the sweet spot, which is very performant, but not too big, such that it's getting hard to handle in practice. The second use case or aspect that we wanted to cover is we wanted to make it as easy as possible to generate. And one issue that you face, especially if you need to generate a lot of text, and that's usually the case when you build something like a code completion model, you need to generate every few tokens. With normal like multi-head attention, your GPU memory might blow up very quickly. And we used a slightly different architectures called multi-query attention, where you don't have too many attention heads, you only have one, and that makes it far more memory efficient. And I'm gonna quickly talk about multi-query attention again and show you a little bit more in detail how it works. The second thing is flash attention, which is a GPU optimization technique that lets you train for longer context without blowing out the GPU memory. And finally, it's quite important when you predict code, for example, predict a piece of code, to have bidirectional context, which might be a bit counterintuitive if you look at the image I showed just before, where I said the model can only look at the past tokens. But if you write code, code doesn't usually just flow from left to right or from top to bottom. You might have a function that's defined further below in the code that you're using inside a class that's defined above. And if the model can only look at what's before, then it might be completely blind to that function you defined, that it might use it wrongly or might just define its own function again when it needs to predict a hole in your code. And there's a cool technique called fill in the middle. And it essentially allows you, even if you have a language model that only, like a causal language model, like the one I showed, where you can only look to the left, to still consider text that comes after the point where you want to predict some gap. And the way it works is you just rearrange the input of the model a little bit. So rather than having all the text flowing from left to right, you chunk it in 3 pieces. You say you have a beginning piece, a middle piece, and an end piece. And you want the model to learn to predict the middle piece. And since you can only look to the left, the way you do it is you take the beginning piece, then you take the end piece, and then you take the middle piece and put it at the end. So the model sees the beginning and the end first, and then it needs to predict the middle part. And that's just like a simple data trick where you rearrange how the text is ordered, and that helps you helps the model predict something that's in between. So I said that we tried to train a model that's not too big, and that was not only motivated by we want to train small models to make it easier, but also by some analysis on the scaling laws. And to motivate that a bit, just a reminder for those of you who maybe don't know what scaling laws are. They're a finding in language modeling that their loss essentially follows a power law as a function of the number of parameters and the amount of data you train on. You can see the formula on the top right. So the loss as a function of number of parameters and amount of data. And you can see it's a power law, and you have a irreducible part of the loss that no matter how much data and how much model capacity you use, you will never get off that last error, but all the rest you can essentially get smaller as you scale up as a power law, as I said. And the initial scaling laws were found by work by OpenAI called now the Kaplan scaling laws. And they found that as you scale the number of parameters and the data, the ratio that you need is essentially you need to scale the model 5.5 times when you scale the data 1.8 times. And that motivated the choice for GPT-3, which under those scaling laws was like the ideal thing you could do to get the lowest loss, which is train a 175 billion parameter model on 300 billion tokens. 2 years later, DeepMind released the scaling law paper, and they found some slight issues in the first scaling laws. And when they fixed those, they found that the actual a better scaling is even when you scale roughly the model and the data equally. And as you can see, that leads to slightly different optimal architectures. So rather than training 170 billion parameters for 300 billion tokens, it might be better to train 65 billion parameters, almost a third as big, and train it 3 times longer on 1.6 trillion tokens. Now, fast forward to today, and if you look at the models that are recently released, like Llama, they actually train for even longer and smaller models. And so one important insight is that compute optimal is not necessarily generally optimal. What these scaling laws tell you is just if you follow them, you will get the lowest validation loss the lowest validation loss for a given compute budget. That's nice, but for example, if you think about putting that model into production, maybe you would actually pay a little bit more training compute if it would make the model smaller. And that's kind of the development that's happening now. And Harm de Vries, who is a collaborator in Big Code, he did some analysis on the scaling laws, on the chinchilla scaling laws, and he found you can actually kind of calculate the trade-off that you have. And I show you here like a plot on how that looks like. So essentially the blue dot is like the chinchilla optimal training ratio. So if you train in the blue regime, it tells you what's the model size and the data, and if you do that, you're guaranteed to get like the lowest validation loss for your however much compute you have. But you can visualize that minimum, and what you can see is that it's a very flat minimum. So if you go to the left or go to the right, if you go to the right, you increase the model size. If you go to the left, you decrease. And what it shows you, for example, is if you go to 75% of the chinchilla optimal model size, you almost pay no compute overhead to achieve the same loss. So the compute overhead on the left is computed in terms of like, how much more do I need to pay in terms of compute to reach the same performance as the blue dot. And you can see the 7B Llama model probably paid 50% compute overhead compared to training a chinchilla optimal model. But the model itself is less than 50% as big as the optimal model. So if you put that into production, means it's more than 50% cheaper to run. And if you look at the more recent Mistral model, which was trained on rumors are 8 trillion tokens, you can see you pay pretty significant overhead. They probably paid 300% compute overhead as opposed to training a chinchilla optimal model. So they could have trained a model that has the same performance, 3 times cheaper, but their model is a fourth as big as such a model. So it's very cheap to run. And we found like the community quite likes that aspect because it makes it much easier for them to fine tune the model. And with that curve, you can essentially calculate what exactly is the overhead you pay and the amount of money you save when you do that at inference time. And there is even, I made an interactive an app, so you can plug in a number, and so number of parameters and number of training tokens, and you can see where on this line you are with that setting. One issue is, I should mention, is as you move to the left, you have to pay essentially by adding more data. So if you pay 300% compute overhead with a model that's a fourth as big, that means you need to have a lot more data to make up for that compute. And the question is a bit, where does that data come from? And there's some recent work which is quite interesting, looking into repeating data. At some point you run out of data. We had, as I said, 200 billion tokens. So the question is, can we only train for 200 billion tokens, or maybe can we train a few epochs? And there is a cool work by a few colleagues led by Nicholas Minninghoff about the impact of training multiple epochs. And what we can see is essentially we can train up to 4 or 5 epochs without getting a significant performance degradation. And that was kind of the motivation then for StarCoder to say like 5 epochs is fine, so we can train 200 billion tokens, repeated 5 times, we get roughly 1 trillion tokens. And if we look at a 15B model, it's a little bit on the left, we almost pay no compute overhead, but it's a little bit cheaper to run. And we trained even a 7B model and a 1B model, which are further on the left. I'm going to skip over multi-query head attention and multi-query attention and the flash attention in the interest of time, so we have a little bit more time for questions. But I want to show how the training actually looked. So we used 500 GPUs, and we needed to distribute the model with tensor and pipeline parallelism. And we trained for 4 million with a 4 million tokens batch size. As I said, 1 trillion tokens for training, and it took about 24 days. And you can see the loss curves on the right, and it's essentially smooth sailing. We see the color changes because we had to restart the training a few times, but that was mostly because of cluster or hardware failures. But other than that, the training was very stable. We then wanted, of course, to know how good the model is. And for code models, there is a benchmark called Human-Eval. It's quite a simple benchmark with 160 programming challenges where the model gets a function header and a doc string, and it needs to generate the function body. And then we have a few unit tests where we can test how often the model generated the correct solution. So we can execute the code and run the unit tests. And you can see StarCoder outperformed all the previous open models. And there are a few models built after on top of StarCoder called Octocoder and VisorCoder. They're essentially just fine-tuned versions of StarCoder, which aimed at like squeezing the last bit of performance out of there. Since then, also CodeLlama has come out, which is a model on top of Llama 2. And since then, StarCoder has been outperformed, but we're working on building the next generation of StarCoder to hopefully close the gap again. We also have a VS Code extension where you can use the model in VS Code. On top of that, we have a membership test. So when code is generated, we can test whether it was in the pre-training data. And you can check what kind of license, for example, that snippet had if it was in the pre-trained data to give attribution and decide about licensing. And one thing I wanted to highlight is that I mentioned before, like if you build open models and open data set, it empowers the community to build their own thing. And for example, we built a stack, and since then there have been 4 models built pre-trained with the stack as well, stable code from Stability, but also models from Salesforce and Replit. They have used the stack to pre-train models. And also, as I said, some people have taken StarCoder and fine-tuned it on to get better performance, or maybe trying a specific model, for example, SQL Coder, which was fine-tuned on high-quality SQL code to get a very good model for SQL, which matches or outperforms depending on which version of GPT-4. So we're currently, as I said, ramping up for StarCoder 2. Hopefully we can release it before Christmas. We're working pretty hard these days to get it out. We built a new data set and going to train a new model. Training's probably going to start next week if everything goes well. And yeah, with that, I think we're in a good spot to answer some questions.
All right, awesome, thank you. Just to mention again, if there are any questions, can you post them in the Q&A chat so that we can read them and answer them. I can start with a few questions that I have. So I think one of the things that you mentioned about this benchmarking and that we don't know what has actually been included in the trained data sets may make it hard to understand. Has the model actually learned, or has it simply memorized this because it has seen it somewhere in the trained data set? Do you have any ideas on how to somehow go around this problem?
Yeah, I mean it's a pretty hard problem, and in code it's also pretty difficult to determine where the line is of considering something part of the training data or not. So we have these benchmarks that, for example, human eval, which is lead type coding challenges about like write a function that sorts a list with every odd number or something like that. They try to make it such that hopefully it wasn't in a lot of code before, so they try to come up with exotic questions, but there are lots of variations that are very similar, right? So it's pretty hard to know. What we did is we removed the data sets that we wanted to evaluate on, and we posted the code and which data sets that were, so people would know. But for other models, we simply don't know. I think there has been some recent work that can help indicate if a certain sample was likely in the pre-training data, but I'm not so familiar with those techniques yet.
Yeah, that makes sense. Okay, there are a few questions in the chat as well. Actually, there are many questions, so let me start reading those. First thing is, how did you figure out 80 languages and not say 50? What made you think 80 was right? What factors did you have to consider?
Yeah, that's a good question. So I think it's very hand wavy. So we had some people in Big Code who are more familiar with programming languages than me. Me personally, I know maybe 5 programming languages and I can write in 2 or 3. But there were some people with more classic computer science background. And so we tried to look at tables, for example, what are the most popular languages last year or so, so that we for sure have those languages. And then we had some people with a deeper background just going over the list and say like, this can probably go, this probably makes sense to keep. And then it was a little bit of judgment call and say like, I don't know, in the order of 100 seems fine. But it wasn't like theoretically motivated.
Yeah, I think that makes sense. Next question is, what is the max size a model can be to be on a single GPU memory, say A100?
Oh yeah, that depends on a lot of factors these days. So depends first of all what precision you want to put the model on. So you can either go full precision, 32 bits per parameter, or half precision, either FP or bfloat 16. Or even more recently, now there's 8-bit and 4-bit quantization where you can quantize the model down to 4 bits. So you save a lot of memory and you get almost no performance hit. And I think with that, then it depends also, do you just want to use it for inference or do you actually want to train? But I think for inference, you can squeeze a 30B model on an A100. And for training, if you quantize it, there's the cool technique called PEF, LoRa, low rank adapters, where you quantize your base model and you just train a very small layer on top. And we managed to fine tune a 7B model on Colab. And Colab offers, I think, T4 GPUs with 24 gigabytes of memory. So you can train a 7B model on Colab. It's going to be a little bit slow, but if you only want to fine tune it on a small data set, it might work.
Yeah, cool. Okay, we have a few more questions. Can you fine-tune StarCoder on a language that wasn't in the train data, and how can we expect this to work or not work?
Yeah, actually you can. Maybe it's not so surprising. It was a little bit surprising to us when some collaborators first tried it, but I think just training it for 1 or 2 billion tokens on a new programming language gives it already like a very decent performance in that language. Maybe the explanation is a bit that if you know 80 programming languages, learning the 81st language is not that hard compared to all the languages that you already know. So it's not that big of a domain shift. And so collaborators have trained StarCoder for a day or two on a new language, and it works pretty well.
Right. Before I continue with the chat, I have another question kind of related to this, but when you say trained for a day or two, how much like hyperparameter tuning is involved in that? Or is it just like you let it run and just after 2 days look at what happens? Like how much thinking should I have to do when I'm trying to fine tune a model like that?
Yeah, actually, I feel like the hyperparameters usually for fine tuning for most transformers are the optimum is very it's a very broad plateau. So as long as you get kind of the learning rate right and you have a lot of flexibility in the batch size, if you use 32 or 64, I mean, maybe you can squeeze a little bit more out of it, but in most cases that I've seen, like it works pretty easily. And I think that's also part of the reason why there has been such an explosion in all these instruction models that the community has trained. I don't know if you've seen, but since Llama, there has been Alpaca and Vicuña and like hundreds of models that the community has trained. And I think one of the reasons is with these techniques like LoRa that I mentioned, which makes it very cheap, and the fact that finding the right training regime is actually not that hard, enables everybody to kind of get there quite easily.
Yeah. Yeah, that makes a lot of sense because in my other experience with neural nets on various kinds of data, most of my time was spent on like hyperparameter tuning. But in this case, because so many things seem to work, I would presume it's less of an issue, but that's very good to hear. Okay, next question, Peter. Git repositories also show you the evolution of the code over time. How can this information be used when training language models?
Yeah, that's a very good question. So for the very bulk of our data set, we just took like the latest Git status, or yeah. So we didn't consider all the history, but we just took like the latest commit on main. But we also generated a smaller data set, only like 30 gigabytes, so maybe 10 billion tokens or so, so 1% of the full training data, which was Git commits. And the idea behind that is that you kind of get an instruction, if you filter it right, you kind of get an instruction data set out of it, because you can think of it like you have a code before the commit, a status of the code before the commit, then you have a commit message, and then you can put the code after the commit. And then the commit message, if you filter it right for like meaningful commit messages and not just like fix or update, then the git commit message can act as an instruction, right? You have the code, and then you say, I don't know, fix the style to match PEP8, or fix the memory leak, and then that gives the model an instruction to do something. So we try to include that in the pre-training data. Now we're trying to go a step further, and we're trying to include pull requests, because in pull requests you also have then human feedback potentially, where people report like, that commit didn't quite fix the issue, maybe you need to also do this, and hopefully that gives also interesting signal.
Yeah, cool. Next question is around privacy. So when discussing sensitive information like PII, such as passwords and API access keys, it's crucial to consider the potential risks associated with revealing the coding style of a specific company or group. Have you considered strategies to mitigate these risks and maintain a secure approach in such discussions?
I'm not sure I quite understand the connection to the coding style. Maybe you can clarify. I can say a few things, but maybe you can clarify in the meantime. But so we remove PII like generally from all code, and we found, I mean, we don't have 100% hit rate, but it's enough for the model to refuse to give a token in almost all cases. So we also instruction tune StarCoder, and then if you ask it like who invented the light bulb, the model will answer with like the light bulb was invented by name rather than giving an actual name. So it seems to work quite reliably, even if you don't have a 100% PII removal hit rate, because like the model learns like in 99% of the cases you shouldn't reveal anything, and that propagates quite well. I'm not quite sure like how that connects to secrets in companies, because we don't train on companies' data. We have a separate kind of a Hugging Face project where we fine-tune StarCoder on a company's data, and then they can deploy it inside their environment, so their code never leaves the company. And then you're also kind of safe, because maybe the model learns secrets, but also the model is only used internally and not revealed to the outside world.
Yeah, okay, that makes sense. Okay, then next question. Any recommendation for inference HW requirements, and are you working on compression mechanisms so that it can run locally?
Yeah, there are many options these days. So StarCoder is supported in Llama CPP, so the C++ library to run models locally, and it's been quite interesting to follow the community where I think a year ago or so, some people started looking into like, what would it take to run, I don't know, a Llama model on your MacBook, and they have improved quite a lot, and now you can run even quite large models locally on your MacBook. A question, of course, is a little bit like, what's the latency? If you just want to use it to chat, you don't need a very fast model. But if you want to use it to, for example, autocompleting code, you need a much faster one, because if you need to wait more than half a second for a completion, then it already feels like very clunky, and you might already start writing, continue writing before the suggestions comes in. Then the user experience gets very bad. So in those cases, you want very low latency. What we mainly use at Hugging Face is a tool called text generation inference, which lets you deploy a Docker image on your hardware with very optimized code for inference, and also allows for quantization.
Cool.
Hope that helps.
Yeah, I think that makes sense. So, other question, from what you've seen so far using StarCoder, what are the main shortcomings of it in terms of writing code? What would you prioritize as a next direction towards better learning? Which I think is indeed like an interesting question. What are the limitations of the current models, kind of?
Yeah, that's a very good question, and maybe I can talk a little bit how we want to address them with StarCoder 2. So I think one of the main limitations of StarCoder 1 is that we only train on, in a sense, on a file level. So we don't train on repositories, but we take each file and we kind of shuffle all the files globally. So the model just generates the code inside one file, but it doesn't see the rest of the repository. And I think this has a lot of shortcomings. One, our model doesn't have any awareness of the libraries that are used or the versioning of the libraries. So it doesn't know if you're using Pandas 2 or if you use Pandas 3, or it doesn't know what version of an API you're using. It just needs to guess based on the code inside the current file it sees. And what Copilot does very effectively, it takes files or code snippets from your repository or open files and passes them to the model when it needs to generate something for the current file. And that, I think, gives it a big boost in accuracy. So in StarCoder 2, we plan to train with repository context. So we take all the files from a repository and concatenate them. And then we shuffle them. And so the model sees related files next to each other. And also at inference time, you can pass it relevant files into context, so it can make a better prediction. And for example, if you think about Python, you could see that the model gets the requirements file where all the library versions are specified, and maybe even a README that explains, like on a high level, how the library should work. And then it needs to make a prediction about a code snippet, and it can use those information to make better predictions. Or also very often, right, you import modules from other files but in the current star coder, it can't actually look at these other files or where these modules are defined. And I think this is one of the biggest shortcomings that we hope to address soon.
Cool. So we have, well, I just want to say we have 1 minute left, but we don't have 32. But let's do one more question if you have time, and then we can end. So final question, how did you determine an appropriate tokenizer for the variety of programming languages?
Yeah, that's also a very good question. I think we trained a tokenizer on a subset on all these languages, hoping that it will pick up like the common syntax in these languages. And I think it's actually a much easier problem than you would think, because the syntax in almost all programming languages has a very large overlap. So you have classes and class names, for example, and they're always kind of similar. And we did recently some ablations, and we can see that, for example, the GPT-4 tokenizer is much more efficient at tokenizing code than we are. The main reason being that they merge across white spaces. So a single token can be, for example, be from NumPy import NP or from NumPy import. And our tokenizer splits on white spaces always. So a token can never cross a white space. That makes it less efficient, but we trained a few models to see if that actually makes them better, and we don't see a performance boost. So efficiency is not the only thing. Besides that, we try to kind of find a middle ground with a tokenizer that's not too big to slow down the model and not too small, such that it can pick up as many features as possible. Yeah, I think that's about as much thought as went into the tokenizer.
Cool. Okay. Let's end it here. Thank you so much. I think this was super interesting, and judging from all the many questions, everyone else thought so too. Yeah, thank you everyone also for attending.
Yeah, thanks a lot for having me. It was a pleasure answering all the questions.
Cool.